Well, good day, everyone. Welcome to another Toolbox Tech Talk this Sunday. It's getting to be the gig for me every Sunday, thinking up something new to talk about. But this one is one of my favorites. Yeah, what we're going to talk about today is microgrids. Now, look, once again, it's time to get serious, take off the sunnies, and turn down the tunes. So welcome everyone. Welcome to another Toolbox Tech Talk here at the Smart Energy Lab with me, Glenn Morris. You're probably joining me from various of my streaming channels, so welcome to those on Twitter, Periscope, Facebook, LinkedIn, that's a new one from last week, and of course my YouTube channel. So you're welcome to add some comments as we go along, ask questions. I'll try and drop in on those comments and questions as we go. Feel free to share the love, you know, the like buttons, whatever, just to show your appreciation. So, yeah, like I said, today it's all about microgrids, and it is one of my favorite subjects because I live and breathe a microgrid. I live on one, and I've lived off-grid most of my adult life, something like 30 years now, and in the last 5 years, I've built a microgrid here on the off-grid community where I live, Muramura Co-op. So this has been a kind of evolving project. Now, I like to call it my accidental microgrid because I never set out to actually build one. I set out to build a training facility where people come and learn about smart energy systems, solar inverters, battery inverters, solar panels, installation standards, smart energy equipment like monitoring equipment, smart loads too, including your hot water services, EV charging, even water making machines that make water from sunshine and air. I've got the lot here. So yeah, that's all pretty exciting. So I'm just looking to see if there's any comments or questions come in. No one here at the moment. That's okay. But feel free just to throw into the comments field any questions as we go, and I'll try to get back to them and answer them. So to start off today, what is a microgrid? I better define my terms here. So a microgrid is where you've got a grid forming system, something that forms a stable grid. Now here in Australia, we use a 50 hertz grid and 230 volt nominal, though you can set it as you wish. We're running at 240 volts nominal here, just helps with voltage drop, etc., and 50 hertz. So that system, which I'll take you on a little tour of in a minute, I did a bit of a walk and talk around the place, a walking tour this morning, just holding my my camera on a little gimbal, in fact just my phone actually, so nothing fancy, and I filmed it. So I'm going to bring that, it's only about 4 minutes long, little walkabout showing some of the components of the microgrid here, and then I'll get into the theory and evolve that theory too. So starting really simply, going through to defining my terms and some of the complexities that you might encounter. So I'd love to know how people are going. Just let me know if you're got any questions or comments. Please throw those into the chat window. I've got to keep looking over to see if there's any questions come in, so I have to cast my eyes across to yet another screen. And so I'm looking on the Facebook land. Okay. All right, that looks like it's not there. And how we got? We've got a fair few people coming in from my Smart Energy page. Hi, everyone. And Solar Trainers and also YouTube, so that's great. So let's go for the tour. And it's a little movie, like I said, so I'll bring that up on screen. I think it's on that one there. Here we go. And I think I can bring myself up so I can talk to you in the corner. There we go. Bring myself on. Great. What we're looking at here is the heart of the microgrid here at the Smart Energy Lab. This system is a notionally 30 kilowatt inverter system built as a power chain. So let me just press play so we can see a little bit more of it. So power chain is a software variation of by Electronic, allowing multiple inverters per phase. So we've got 2 inverters per phase, 2 5 kilowatt Electronic SP Pros, and they're backed up by what we jokingly call the Tower of Power. It's a Power Plus Energy smart BMS eco batteries. There's 80 kilowatt hours of storage there. So I'll just pause that for a moment. So that system that you're looking at is the heart of the microgrid. If you're wondering what the box on the right is, that actually is a Schneider 600 volt 80 amp MPPT. It's not yet connected. That's going to be our, well, we're actually changing it to an all-Australian room actually with the AERL MPPT very shortly. So that one's just being decommissioned and moved to another part of the training lab. But the purpose there is to have both DC coupled charging and AC coupled charging. Now, one of the reasons for doing this, I'm going a little bit early on the tech here, is that in a pure AC coupled environment, you're very reliant on the microgrid battery system keeping the inverters on. Now, if the inverters shut down for any reason, the whole microgrid shuts down, and you can't even charge from any AC coupled sources because they all require a stable grid to connect to. So having some DC coupled charging is kind of a safety belt, really, that you can always charge that battery from the sun, and therefore that will bring the battery inverters back to life, and then the whole microgrid comes back up and magic happens. So here we go, walking a little bit more and into another area. So what we're looking at here is the managed AC coupled solar inverters. These are 20 kilowatt Select Sun. They're a really nice match with the Selectronic system. They're actually Selectronic certified. That means they have a comms system, and I'll talk about how that all works in a bit. They have a comms system that allow those inverters to be power managed in millisecond accuracy. So the SP Pros, which are the heart of the microgrid, control those 4 20 kilowatt Select Suns, can determine what their power output is. We haven't quite yet finished this build, so you can see there's no cables connected to the bottom of them. COVID has slowed us down a bit on this part. So we're building a 70 kilowatt tracking system. It's a project in partnership with Architect Solar, Longy Solar, and my company SolarQuip. We broke ground actually a few days ago and put the first bunch of piles in the ground. This is a 90 meter long single axis tracker. So it's a long pole that rotates from morning to night. There's actually 2 trackers. With the second tracker, we hadn't put the poles in yet. That's an EV charging point that's going in very shortly, and that will be a smart charger. And I'm going to show you some of the houses to get an idea of what's connected to the microgrid. So all these houses have their own solar and battery. This house is like 7 kilowatts of solar. It's got a couple of solar inverters and a battery inverter as well. This is my house. We've got about 10 kilowatts of solar in my house here, and some smart loads. You can see a Energy Smart Water PV powered water heating system there. This is a tiny house also connected to the to the microgrid. A tiny amount of PV, only really about 800 watts of PV on this system, and that is the Death Spiral accelerator that powers the tiny house. It doesn't export power. Export back to the microgrid. So this is a load-only part of the microgrid. It only can take power from the microgrid. This is a small, back of my house, this is a small system here, the Alpha ESS, well, not that small, it's a 5 kilowatt hybrid inverter with PV. And this is a 9 kilowatt 3-phase AC Thor. It's a smart hot water service in the sense that it's smart because it responds to frequency and can adjust its power level. And this is the DC powered hot water service with an AC boost as well. So you can see there's a lot of different components to a microgrid. It's not just all about generation. It's also about smart loads to soak up generation, because if you're not connected to a utility grid, you effectively are the utility, and you want to find ways of using all of the energy. So there's a big pan coming out from the center of the cluster where I live. There's 30 homes on this off-grid community. It was founded, Murumuru Co-op was founded back in 1974. This cluster, Wombat Hollow, is all connected by my microgrid. So there's 7 homes on this microgrid. As you can see, they all have solar and batteries. There's a mixture of interactive, that means they can export as well as import from the microgrid. Some are import only, so they effectively use the microgrid as their generator backup. Some have smart loads, such as hot water services. Some have dumb loads, such as hot water services with a switch. When I say smart loads, that means a variable load. And there's also a lot of monitoring, so I'll show you some of the monitoring associated with this system. The location, if you're not familiar, this is Mount Tulibawong. Not many people have been there. It's about 65 kilometres east of Melbourne in the Yarra Valley. Behind that mountain you can see there is the Yarra Valley, the wine growing area near Melbourne's east. We are surprisingly considered Metro Melbourne, so we've been in lockdown for months. It's not such a bad place to be locked down, especially with all the land around us, and I've got a couple of young kids that have had plenty of space to explore and play, so that's been really nice, even during lockdown. As a result, I've been doing a lot more online training like this, providing content to my students and just to general viewers. So that's the Smart Energy Lab from the air, plus the homes connected to it via the microgrid. So I'm going to bring up a little picture here to show you just technically what it looks like. So this is a very simple single line diagram schematic of how everything's connected. Now, if you're not familiar with single line diagrams, there's no plus and minus or AC and DC separate. We're just basically drawing lines showing how things are connected. Those three slanted lines indicate three-phase circuits and single slashes, single-phase circuits. You can see there's those 4 Select Sun inverters on the top left, which are the main tracking systems that are being built out in the paddock at the moment, the 70 kilowatt system. It's connected to the microgrid backbone, where we've got the 6 5 kilowatt Selectronic SP Pros in power chain configuration, connected to the Tower of Power, the Power Plus Energy Ecos with the new Smart BMS. It's actually a pre-released version. A lot of the systems come here as the final kind of field testing before they're released to market, so we can do a little bit of tweaking and understand the characteristics. So I might bring up some of that monitoring as well later on. So just a reminder for those who just joined us, please feel free to put some questions or in the comments field, and and let me know how it's going. So thanks there, Bradley. He said it's worth it just for the music. I was very careful to make sure it was royalty-free music, care of YouTube, so I wouldn't get into any trouble. Yeah, so thanks there, Bradley. And I'm just looking over at LinkedIn, see if there's any questions in that land. That's all good. And in YouTube land, no questions in YouTube. Okay. So, yeah, that's the microgrid layout. And you'll see that there's 8 homes. Actually, there's 7 at the moment, but there's about to be another one tacked onto the end. They all have their own battery systems as well. I haven't actually shown that in this diagram. I've just shown them as inverters with solar panels, but they've got inverters, solar panels, and batteries. And there's also about 20 systems in the lab. The lab consists of about 5 or 6 buildings. In fact, we're just about to get a 7th one going, where a lot of equipment lives that's being tested and installed by my students. I'm not actually running any courses, physical face-to-face courses at the moment here at the Smart Energy Lab. We're doing them all virtually online. If you're interested checking out any of my online courses, I've been running every couple of weeks actually a 5-day solar and battery course, which is 4 hours a day. So basically in the morning each day. It's fully interactive Zoom course where you can talk to me and the other students. We have assignments and we go through the process of designing and sizing and the compliance requirements around installing solar and battery, whether it's on-grid or off-grid. That course is offered through my website, solarquip.com. If you go there, you'll see there's a training tab, solarquip.com. Also, I'm starting to do inspector training courses. I've got one for New Zealand inspectors actually coming up the week after this, and that starts at the brave hour of 7:30 a.m. in New Zealand, which is 5:30 here. So yeah, just check out that site, solarquip.com, if you're interested. I'll put a link to it in the comments later on after this live's finished. Yeah, so let me take you into a bit of theory now. Now I'm going to jump over to my drawing tablet. So over here, we're looking at something called frequency to power mode, frequency response to power mode. Now, this has been a requirement in our inverter standard, 4777, see it here, 4777 Part 2, since 2015. Now, it's pretty important to note that date because prior to 2015, it wasn't mandatory to have this mode enabled in inverters that connected to a utility grid. They basically had a binary option, which was if the frequency goes outside of two limits, typically it was like 45 hertz to 55 hertz. If it was outside of that range, disconnect within 2 seconds. So I call that binary. It's either on or off. There also was a voltage range. It was adjustable, but it could be as high as 270 volts on a single phase installation before it would disconnect. Now, with the revision of 2015 of our inverter standard, ASNZS 4777 Part 2, and for those of you from New Zealand, every inverter that comes to New Zealand and Australia will already be compliant to that standard, even though you're still working on an earlier version ratified in the New Zealand electricity regs, which is a bit weird, but the products that you can buy are certified to the 2015 edition. So one of the big changes was that we mandated a frequency to power response mode. And I've tried to draw it really simply here, just showing that across the bottom here is frequency. So we're a 50 hertz grid here in Australia and New Zealand. And if there is a move to 50.25, then the inverter, the 4777 compliant inverter must start reducing its output power in proportion to frequency. So it's a linear relationship till basically zero power at 52 hertz. Now, you will find that the Australian and New Zealand grid doesn't actually move in frequency, but this is where it comes in really, really handy for microgrids, because many quality battery inverters have the ability to shift frequency based on the battery voltage. So if the battery system state of charge or voltage are above a certain level and you need to curtail the amount of generation connected to that AC coupled battery inverter, then the battery inverter can raise the frequency. Now, it is the grid. Remember, in a microgrid system where you're not connected to a utility grid, the battery inverter, the grid forming inverter, is indeed the grid. So if I just go back to my single line diagram, so I've got a pointer now. So the 5 kilowatt Selectronic SP Pros are the grid forming system. So that's where the frequency shifting will occur. It will occur as long as the backup generator isn't running. So you might notice there's a 22 kVA diesel genset as a backup service. Now, as soon as another source comes online, it will set the frequency as well. So the system will follow the frequency of that other source. Now, ironically, that could be replaced with the utility grid. You could actually have a system here where you're a grid interactive microgrid, and therefore, instead of a 22 kVA diesel genset, you've got a connection to the utility grid. It's a little bit more complicated, but it still works. So there's a lot more in terms of compliance that you need to consider, certainly when it comes to reverse power. So just going back to this picture here. So this requirement to ramp down with frequency comes in really handy for connecting standard grid tie inverters to a microgrid, because they don't have to be anything special. They don't need some special microgrid mode, though some inverters do actually have that feature. I know Fronius have the MG50 and the MG60. MG50 is for 50 hertz grids. MG, I presume, is for microgrid, and MG60 is for 60 hertz microgrids. Effectively, it's still a similar regime to 4777 Part 2, but it has some more microgrid friendly features like faster startup, ramp up and ramp down, or maybe more adjustment there. But if you get any 4777.2 compliant inverter and connect it to a microgrid, it will be forced to respond like this with frequency. So what does that mean? All right, well, I'm going to come back to this in a second. I first want to define some terms. So let's have a look at this. This is a generic AC coupled solar system on grid. Now I'm starting with on grid. So this is our symbol for our utility grid here, and we're connecting a battery inverter that has 2 battery ports. Now that's not a very common feature in inverters, but some of the larger inverters or more sophisticated inverters specifically designed for off-grid applications often can be used on-grid, and they have 2 ports. They have a source port, which is could be a generating set, or it could be the utility grid if it's compliant to that standard, and they have what's called a standalone port, so a port that they can continue to provide a stable output to independently when this is not available. And it can also parallel. Now you might notice I've drawn a couple of contactors on here. These are kind of important. I've made it super simple. You can see there's an AC symbol and a DC symbol. That's to represent an inverter, something that converts, in this case from DC, you've got a DC battery system here, and convert to AC. But internally, that piece of equipment will have a couple of contactors. Now, one of them, this one here, is the 4777 grid protection contactor or relay. So it's a requirement of the standard that you have a redundant set of disconnects between the utility grid and the inverter's interface with the utility grid. So that will be operated by the inverter under conditions such as the grid is within range of frequency or voltage. And whereas this contactor here is when will the inverter function, which means the ability to convert from DC to AC, parallel with another source. So this is the parallel contactor. And it's pretty special, really, because if the grid is operating in a sine wave like this, okay, so we'll call that grid. That's the grid. And your inverter can create its own matching frequency. But initially, it might start off, the inverter's frequency might be actually out of kilter, so it might be more like this. And they don't match up. The peaks don't line up. That peak there doesn't line up with that peak there. So the battery inverter actually shifts its frequency and waveform until the 2 line up perfectly. And so cross that one out, they get them lining up perfectly, and at a 0 point crossover, so if I draw an axis on time, at a 0 point crossover like here, they cross over, they connect, and so this parallel contactor will close, and there'll be no reverse power, there'll be no sudden change in characteristics. So it's a very smooth connection. So this is for the inverter function within this piece of equipment to parallel with another source. So far, so good. Just checking to see if I've got any questions coming in. So I'm just going over to Facebook land. So I don't know if I have to refresh, but there's no more questions there at the moment. And I've just got a question in. Yes, Anthony's asking, is there a video recording? Yes, so all of my lives are available via whatever channel that you're watching them on after this event. So don't worry if you have to leave at any point. You'll be able to watch this immediately then when it's finished. So let's have a look. Still no comments in YouTube, which is surprising. Does anyone on YouTube land just say hi? I'm just kind of wondering why I'm not seeing any comments coming up. And sometimes I have little technical problems with my comments fields. I can see there's quite a nice audience out there. So yeah, we've got someone coming in via Periscope. Hi Periscope, you're my first Periscope guest, I think. Welcome. And thanks ProTune Lights. Great. So I got a hi there. Great. Feel free to throw those questions and comments in because I will come back to them after I've done each little piece here and elaborate on them. So coming back to my drawing, let's move along across the output. Now, I call this the standalone port of the battery inverter, meaning that it works independently of the grid. Now, this is a AC coupled system. What am I talking about when I say AC coupled? AC coupling is how does the renewable energy from the PV array get to, which is DC, to the battery storage, which is DC. It gets there through an AC network. This is an AC network. All these purple lines are AC and the orange lines are DC. So it's transmitted through an AC bus, and therefore it's what's called AC coupling. So in the middle here, we've got our switchboard. So this would be where all the circuits that are being supplied have to be. I've called them essential circuits in that these circuits will stay live independently of the grid. So even if the grid fails, this battery inverter can continue to supply through its standalone port these essential circuits. Now here's where it gets a bit special. Not all inverters can have a solar inverter connected to their what you call their backup or essential circuits port. This is a kind of special feature that this solar inverter can output energy, see it's a one directional arrow, and that energy can flow in the reverse direction back into this battery inverter and either be exported to the grid or used to charge battery or both. Now, don't try this unless you know the product actually can do this. I have accidentally done this with a fairly generic product, and yes, the smoke did come out and it wouldn't go back in again. So you need to use a product that's designed to be able to take reverse power flow and effectively reverse the conversion process. It takes AC and makes DC from its standalone port. So why have I put in here frequency shift power control? So this is the simplest and you could say easiest way to implement control of another generating source, such as the solar inverter, whenever the grid is not present. So if the grid is not present, so let's cross the grid out. So I've crossed the grid out, the grid is gone now. At that point, this grid protection contactor will open, and it will not be paralleling with the grid because the grid may actually come back suddenly or it's dropped out of frequency or voltage. It's opened this contactor, and it will still monitor this port to see if it's within range, but if it's not, it'll keep this contactor open and it will carry on supplying power. Now this parallel contactor, if it's closed when that happens, will continue to supply power to the essential circuits. There may be a small step change. So for instance, the nominal output voltage of the inverter in standalone mode may be 240 volts AC. So it's a single phase. And the grid may be 245 volts because of, just it is. Australia has terrible voltage regulation on our main grids. So that might be at 245 volts. So the moment that the utility grid disappears, there'll be a small drop to the nominal voltage of the inverter. So that 5 volt change isn't a problem, but it is actually a change. So there'll be a slight variation as a result of loss of grid. It may happen depending on load during a high load transition, and that can cause a small interruption. So generally this is not deemed to be a totally uninterruptible power supply. It's not continuously online. There is possibly up to 10 milliseconds in this configuration for many of the inverters that can do this, where you may have a small interruption. Now that's very, very short. So let's carry on. The grid's gone. We're now running as a standalone system, but we have a problem. These batteries are at 100% state of charge, and it's a sunny day. It's the middle of a sunny day, and we've got, let's say, 5 kilowatts of power pumping in. Where's it going to go? Well, obviously, it's going to go first to the essential circuits. So let's say 1 kilowatt is going to loads in the installation. Where are the other 4 kilowatts going? Well, this is where frequency shift power control comes to the rescue. It allows this battery inverter to say, whoa, 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 I don't need 5 kilowatts of generation. I need 1 kilowatt because my batteries are full and the loads are consuming 1 kilowatt. So it will change the frequency using this strategy. Remember, it will say, I don't need 5 kilowatts, so that might be 5 kilowatts here. I only need 1 kilowatt. So please reduce to 20%, and I'm going to raise the frequency to, I don't know, 51 point something hertz. So it will just raise the frequency of itself when it's islanded from the utility up to this frequency, reducing the power output of all connected solar inverters to 20%, and therefore not overcharging the battery. So yes, Giran asks, so you can change the frequency, right? Well, very special condition, Giran. You can only change the frequency when you're not parallel with the grid. You can't change the utility grid's frequency. It's the monster that determines what the frequency of millions of homes are. But whenever it's islanded, so this only happens when you've lost the utility. So the utility grid's lost, then this frequency shifting power control can occur. I'm just going to check questions and what else we got here? Okay, just looking at LinkedIn and can't see any comments there. So the first time I've actually used LinkedIn. Oh, there is comments. Sorry. Thanks very much. Saif. Saif is assisting me here from the LinkedIn side, just keeping track of questions, and so he's put a link in there for those on the LinkedIn platform where you can watch my videos on YouTube. That's kind of my main platform, but I also stream to Facebook, Twitter, and LinkedIn, of course. I'm just checking the other comments here. Sorry for this slight interruption. And Ray gives me the correct answer. Thank you, Ray, of 51.6 hertz. I love it. Brains trust. There we go. At 51.6 hertz, we'll be at 20% of the power rating. So that shifting is what makes this all stable, allows this to happen safely, that the grid can disappear, but we can still charge our battery with solar by controlling the solar inverter. Okay, I'm taking this in kind of small steps because the next step is going off grid. So the only difference really in the diagram from the previous one is I've replaced the grid with the generating set. So this generating set is a unidirectional device, hence the blue arrow only points towards the battery inverter, so it can only supply backup power. You can't absorb power. Unfortunately, you can't send power to a generator and make diesel. It's a one-way process. So, because that's a one-way process, this contactor here has got a different purpose. This is actually a reverse power protection contactor. That's there because generating sets, though some of them have built-in reverse power protection, hate it when you try to turn them backwards, because that's what happens if you reverse power flow into a generating set. So this now, instead of being the 4777 grid protection contactor or relay, is actually the reverse power contactor. And the same story, this is the paralleling contactor, which determines when the inverter function from its own DC battery source is allowed to parallel with another source. Now, this is a great feature because it means that for off-grid, you can actually have both the generator and the power of the battery inverter working in unison. So let's say we've got a 10 kVA generating set here. Let's say it's diesel, so it's probably going to be putting out 7 to 8 kilowatts of power. And let's say this is a 5 kilowatt battery inverter. So we can actually add this plus this to supply loads. And that gives you the ability to bring on, when there's a high demand, the support of a generating set. And if the loads start to drop away again, then the generating set can be charging batteries at the same time as supporting the loads. So you've actually got the perfect way of using a generating set, particularly a diesel generating set, which is they'll run at a constant load. They're not going to be seeing loads go up and down and the horrors of light loading, which causes significant issues with generating sets. So that's a little bonus. But what happens over here is the same thing: frequency shift power control. If the system's designed appropriately for off-grid, you won't be running the generating set all the time. It will be really there as a backup source for either where there's insufficient storage in the battery system, or the power demand is above the inverter's capabilities. It's above 5 kilowatts for extended periods of time. That's when that will run. But most of the time, you'll be running just off the battery inverter, and when the sun comes up, the solar inverter will start producing, and you'll have to be able to control it. So once again, we get the situation where the batteries, let's say early afternoon, reach 100% state of charge, and we need to reduce the amount of power coming off the PV array, so we shift the frequency, and we do that using that process again. So we just basically, when I say we, the battery inverter shifts its output frequency along this trajectory, and therefore controls the amount of power being produced. So it's not burnt off, it's not wasted, it's not turned into heat. It's actually just not produced. And people often ask, how does an inverter stop the solar panels producing power? Well, it's the wrong question to ask. How do solar panels produce power? They get power sucked from them by the solar inverter. The solar inverter is effectively, sorry for using technical terms, the solar inverter is a smart load. It determines what the input impedance is on the DC side of the solar array, and therefore how much current it's going to draw, and therefore at what voltage the array will operate. So it's actually got its hand on the dial and saying, solar array, I want this much power, up to the maximum you can produce. And it can say, I don't want X amount, I want less. So the solar inverter, by adjusting its input impedance through its maximum power point tracker, can control the array to produce the power required. So there's no burning off of surplus power. You could say it's a waste. It's not burnt off, but it's a lost opportunity. The sun was shining and you're not capturing it all, but that's inevitable to some extent. Thanks, Ray. Yeah, Ray is pointing out the factor of 0.8 for a diesel generator is fairly typical. 0.75, 0.8 is what my diesel experts tell me. That's kind of what I use on my systems. It gives really good fuel efficiency as well. So let's take this a step further, and hang on while I'm looking at the comments field, and I think in Facebook land. Let's have a look. Where am I? I seem to have clicked on the wrong Facebook page. There we go. No more comments in Facebook land. Got one thumbs up. Boo-hoo. And in LinkedIn land, no more comments there. Great. So it seems that the YouTubers are the ones who love chatting to me. Thank you. Thank you, YouTubers. All right, so let's move on. And now we're looking at a slight variant. I'll just jump back again. Off-grid, AC coupled solar. Note that this is a PV array solar inverter here, and this is a battery inverter. Now we're swapping it for a hybrid inverter. Now, in the sense that hybrid has battery and solar and can use another AC source. So, and this is, you'll notice, a symbol for a battery, and I've said it's a 400 volt battery. It depends on the hybrid inverter, but we're seeing for domestic hybrids, high DC voltages are starting to become more popular, though there's nothing wrong with, the lower 48 or whatever. It's just that this is becoming a bit more common, and the PV array. So this system works in exactly the same way. Ray asks single and three-phase. Yes, all of this doesn't really matter whether this is a single-phase system or a three-phase system. I could just as easily go ///, meaning that's a three-phase diesel generating set, with three-phase output power connected to a three-phase hybrid inverter. But actually, that doesn't have to be a three-phase hybrid inverter. That could be a single-phase hybrid inverter. It would just be supporting only one of the phases. Now, phase imbalance is something to consider in a system where you're not generating at three-phase, but that is just a design consideration. So let's extend this. It's once again AC coupled. We're using frequency shift power control, as I've pointed out before, to control this inverter. But this hybrid inverter has another trick up its sleeve. It's got its own battery. So it can be told to stop exporting power. I've shown this as a double-headed arrow. It can be told to stop exporting power back to the switchboard, or reducing the amount of power that's exporting back to the switchboard by frequency shifting of the main battery inverter. But it can then still, because internally it's DC coupled, it can send solar power into its own battery. So it can be a bit more of a buffer. It can still soak up. And this comes down to how this is programmed. Is it programmed to first use solar, second use its own battery, third use, we're getting into microgrid territory here, but we'll just call this another source. So, next one. So I'm building this progressively before it gets a bit more complicated. Here we've got a AC coupled microgrid system off-grid. And I've used the word microgrid, meaning that there can be multiple inverters connected to multiple installations. So I've just shown this as, you know, a three-phase, a single-phase, and a single-phase inverter, and I've even shown them as three different types. This one here is just a solar inverter. This one is a hybrid inverter with its own battery, and this is a battery inverter with no solar. Now, I haven't shown the load side of these systems, but these three inverter systems presumably would also be associated with one of the installations, like here at the Smart Energy Lab. This would be some of the houses connected to the microgrid with their own systems. And if you look at the little arrows that I've drawn, a solar inverter, oh gee, I put the arrow on the wrong side. I just realized it should be there. A solar inverter can only export energy. Oh, embarrassing mistake. Quick. Can only export energy. It can't take AC power, create DC, and therefore create sunlight. It's a one-way direction. There you go, live error correction. So it's only going to export power from the solar, whereas a hybrid inverter's got a double head arrow. That means it can import from the microgrid, or it import, sorry, from the microgrid, or export to the microgrid. And lastly, the battery inverter down here can only use the microgrid as a backup source. So there's no solar drawn on this one. You'd think, well, that's not so good. There may be some DC coupled solar as well. So I haven't drawn that, but there might be some solar directly connected through its own maximum power point tracker. So we've got a maximum power point tracker here with its own solar. So there may be some DC coupled solar on that system. And it's therefore just using the microgrid as like a backup generator. Now, one of the big pluses about a microgrid is not just the ability to distribute energy around a number of houses, but is that they can share energy between them. So for instance, when this system, let's say this is a big one, let's say there's 10 kilowatts of solar on this house, and they're a quite efficient home, and so by 11 o'clock in the morning, their batteries are full, and that 10 kilowatts is effectively going to go to waste. They can start exporting back into the microgrid energy. Now, in a AC microgrid, all of these lines are joined together. See the dot there? And they all join together. So energy will flow based on an impedance divider network wherever it needs to. Therefore, it can surplus from this house can go to this one, surplus from this one can go to some sub-circuits here, etc. And the main battery system will just augment that. So you get a kind of a flatter distribution of energy. You don't have just one house having too much or too little. It starts to even out across a number of installations. I call them houses, but they may actually be any sort of facility. Just looking down at the questions, Gieran asks, hybrid with battery supporting battery inverter. Isn't it bad for efficiency? Well, efficiency is what it is. You might say, why would you want to support this system with another battery system? Well, first up, solar energy is the source is free. So far, no one's taxed the sun, apart from Turkey, I believe. There's actually a tax on sun. But no one's taxed the sun in Australia or New Zealand, and therefore it's a free source of energy. So in a way, efficiency doesn't matter if you have surplus. So if you've got surplus energy, you might as well do what you like with it, whether it's charge batteries, supply loads, and we'll get to this in a minute, have discretionary loads that you can turn on and soak up some of that surplus. But I agree with Gieran, you don't really want to charge one battery to charge another battery as the normal step. You actually want to use that battery to buffer demand. So we're not designing the system so that this hybrid inverter charges up this battery during the day and then charges up this battery during the night. It would be, two losses, but they're not huge. 5% and 5%, you've got 10% loss there. Kieran says you have tax on batteries, I'm sure. Yes, definitely. Batteries are not a generator. Batteries are a storage tank for energy, but solar PV, the source is the sun, and the sun doesn't have a tax on it. That's what I'm getting at. Okay, so Ray, let's have a look here. Ray says, got to resize my screen all the time. Ray says, suggest using smart home to watch the power of all appliances and turn on loads to make use of the extra power. Absolutely agree. And we'll get onto that in a minute. We'll start looking at smart loads next. So I'm going to make a move now. I've been talking about this frequency shift power control because it's built in to 4777 as a mandated requirement for all solar inverters. That means this feature since 2015 edition of the standard is just on by default. And so that gives this design, it's very simple. These do not have to be the same brand. These can be any brand. And as long as they comply with that standard, they'll work together in frequency shift power control mode. Now, there are a few caveats about this in terms of design. There's a power ratio that you need to observe. And the power ratio is how much energy can the battery inverter absorb coming from AC coupled sources. And that power ratio is determined by the battery manufacturer. The inverter manufacturer. They might say, in AC coupled with generic, we call this generic frequency shift power control, 1-to-1 ratio. So that may mean if this is a 20 kilowatt inverter, we can have 1, 2, 3 summed to 20 kilowatts. It can't absorb more than 20 kilowatts. Some may have a higher ratio. And the reason for that is that frequency shift power control is not fast. It's a target. It says try and reduce now to a certain power level, but it doesn't happen instantaneously. And when you're dealing with batteries, particularly high performance batteries, some of the lithiums are very, very tight on their maximum voltage, and you go over that for a split second and they shut down to self-protect. So you've got to be able to control power flow pretty precisely. And if you've got this ratio wrong, that can be a problem. You just might have shutdowns or even failure of your system. So check with the battery manufacturer what the maximum ratio is when in frequency shift power control mode. So last of these drawings is managed AC coupling. Now, it's a term I'm using. It's actually Selectronic's term, and I like it, which is the management is done via comms. So you'll notice here, very similar. I've just kept it super simple, and I've actually drawn more or less what part of my microgrid is. These would be, for instance, the 4 20 kilowatt Select Sun inverters. I've got only 30 kilowatts of 3-phase battery inverter power, but I've got 20 plus 20 plus 20 plus 20. So I actually got 80 kilowatts of solar inverters connected to the same grid. And so the ratio is more than 2-to-1. 2.5 to 1, I think. So why can that be done? Because communication allows for very fast control of power. Basically, the battery inverter commands the power output of these in sub 10 millisecond intervals, and just says reduce, 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 increase, 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 etc. And all of these, which are daisy chained together, respond as one. And so you'll have a master which is connected by comms to the battery inverter and the slaves, and they will all work very fast. And you can have, I'm not sure what the limit is, it might be something like 5, I think, in Electronic land connected in this arrangement. So having a managed AC coupled system gives you the ability to really extend that ratio of power. So we've got about, I think, 90 kilowatts coming on soon connected to this system, of which 80 is going to be, it's actually 70 kilowatt peak watts of panels. So 70 peak watts of panels is managed, and we'll have a residue of generic, approximately 20 kilowatts of generic. So still rely on a little bit of frequency shift, or what's sometimes called frequency kick, which is if in doubt, just raise the frequency to 55 hertz and get rid of any generation instantly. So that's how we got to using managed AC coupling as a way of having a lot more power connected to, generating power connected to the central battery system. So I'm going back to my original single line diagram just to remind you how all this was put back together again. And while you're looking at that, I'm just going to check my comments. Not quite sure what you mean, Brad, but anyway, don't say that too loud. So Guerin points out single point of failure on battery inverter. What will happen if the battery inverter goes down? So you're referring to the grid forming battery inverter system. Yeah, you effectively have the same problem that utility has, which is if the utility stops supplying your home, the lights go out. So when you're building a microgrid, you have the microgrid side is a single point of failure, but, and Guerin, this is the good news part, all of those client systems, which are homes with their own solar and battery, don't lose power. So this is one of the great strengths of a grid paralleling microgrid, sometimes called a mini grid. So it uses the grid as an adjunct, and the homes have their own independent systems, and the grid is there to top up for surplus. But if the grid fails, all those homes are still online. Now, this is being trialled in various parts of Australia. So I know AusNet in my area, AusNet Services have been doing this in Mooroolbark for some time now. We're taking a whole street and making it into a microgrid. It means there's a lot more resilience into the network. So if there is a storm and a loss of power, those homes don't all black out together. They'll run on their reserve capacity. So you do get greater resilience with a microgrid. And it's kind of easy to reticulate too. You can just keep adding to it based on the rules around maximum ratio of power to generating power to battery power. Okay, so thanks, Guerin, for asking that question. Just checking my LinkedIn questions. And go. So I've got a few comments. Let's have a look. Oh, great. There's a whole bunch in there. Thank you, Lance. Thank you for that. Are you running overhead conductors to power the other houses? No, everything's underground. We're in a sort of forested area and trees and things. I hate seeing overhead lines. So yeah, it's all underground power. It does make for a fair bit of digging, but we're kind of lucky. We've got an earth moving guy here. He's got trenching machines. He just loves digging trenches. And looking down here, thanks, Saif. Saif asked, how about using the new hydrogen storage instead of a battery? I'm very keen to try any technology that's safe and moderately proven. So yeah, I'll definitely be keen to try some hydrogen storage. So it's not here yet. That's kind of what the Smart Energy Lab does, is we trial a lot of early release products for standards compliance, for instance, and market suitability, but also feedback on the experience of installing them, because often my students and my electricians who are working on these systems will give feedback to companies about their products before they release them to the market. Great. Ray, would a token comms be better than a daisy chain based on latency? Sounds like, Ray, you're an IT guy, so I remember token systems before. Yep. Latency isn't a big issue when it comes to managed AC coupling. 5 milliseconds is plenty fast enough to control those inverters. But yeah, if you had a large number, and that's probably what you're pointing about, instead of daisy chaining, but a common rail with tokens that have intervals, then that would be better for large numbers. But I think that's outside of the scope of what I'm talking about. Yep. Okay, so what I want to do now is just show a little bit about monitoring, because monitoring is a really big part of making this all work, or at least understanding how it's working. No, wrong screen. What you're looking at here is a interface to my monitoring system platform produced by Switched In. So Switched In, whose lovely logo I'm hiding, unfortunately, is a company who's award-winning company here in Australia for their smart energy management systems. They've won contracts with some of the major utilities like Horizon Power. They are really great at being an independent monitoring platform. So here they've got, I think I've got about 16 or so. Look at that. That's the list of systems that we've got monitoring on. Because it's a lab, things change all the time. So some things are offline, some things are online. And at the dashboard level, so this is my dashboard for my lab, I get an overview of the last week or so, and I can look at the generation profile over the week. I can look at loads as well. I can look at battery state of charge across all of the systems on the microgrid. And I can look at grid-sourced energy as well. Going over to one of these tabs, so I'll click on the microgrid system in the list, and now I can burrow down and look at exactly how it's performing. Now, this morning we actually identified a problem from the monitoring. So we noticed this strange thing happening, which was about 3.5 kilowatts of load coming on and off. It's almost clockwork. Look, boom, boom, boom. What's doing that in the middle of the night? So it was, started at 2 o'clock in the morning and was running through. Now, because a lot of stuff changes here in the lab, sometimes circuits are repurposed and get connected to places we forgot there was a load on, and it turned out that there was a hot water service that wasn't being required that was switching on and off, soaking up a lot of power. So this gives the oversight of the network to allow us to see when there is a problem. Because remember, energy is precious on a islanded microgrid. We don't, precious in that if we run out, we have to use a backup generator, and that uses fossil fuel, and that's not a good thing. So this diagnosed this problem. Now I can turn on lots of other parameters. It's just insane how many things they monitor. So I might be interested in something else. I might be interested in, for instance, the power on each of the phases. And so I can look at the phase balance here. And straight away, I can see there's, it's all on one phase, that big lump. It's on the L1 phase, and I can see that the generation is very mixed. I've got a lot of generation on the L2 phase, but not much on L3, and virtually nothing on L1. So probably need to look at phase balancing a bit better here. Another thing that we can do with a smart monitoring platform is control, and Switched In produced this device for me, which is basically a relay control board. I can turn on and off with a click through the cloud. This is all cloud-based. You can probably see from the URL. From the cloud, I can turn on and off different relays. These relays control loads, so I can turn on and off things like, hot water heaters and ancillary appliances that may or may not be needed. They can also be scheduled and controlled by other parameters, such as frequency. So having a control system is another great feature. And last one, looking at a a small AC coupled system here. It's a Victron Quattro 5 kVA with a Fronius Galvo. I just saw that Galvos have just been retired, so it was the last inverter on the market that was galvanically isolated. Well, I've still got one here. And here I can see the mixture of energy, and I'm looking at PV power in green, load power in orange, and grid power in blue. What that's telling me is I'm using no grid power at all in this system. So this is one of those client systems, and it's more or less meeting all of the load energy from its battery system. Thanks, Ray. Is there an option for if this, then that? I noticed if this, then that. I think now charging. Not sure the answer to that question, Ray. In a way, that is kind of what Switched In do, is if this, then that, with their own platform. So they're a smart management system. So for instance, an example would be if there is surplus generation and the frequency is rising, which is an if, then turn on a discretionary load to soak up that surplus, and that's the that then. So yeah, they definitely do pretty much the same kind of thing through their monitoring platform. So just we've come to the top of the hour, and I've kind of talked about my favourite subject, which is microgrids. There's a lot to be said about them, but I guess I wanted to communicate that it's not rocket science. There's a few basic rules that you need to consider in terms of products that are suitable for interacting with each other, such as the battery inverter being able to accept bidirectional power on its standalone port. That's a pretty important consideration. I mean, to mention some brand names, you know, SMA, Sunny Island can do this. The Schneider XW Plus can do this. Studer XTMs can do this. The Victrons definitely can do this. They're whole range of Victrons that can work in AC coupled mode and frequency shift. And of course, Selectronic, those will be some well-known brands that are capable of this feature. Contrasting that with a lot of hybrid inverters designed for the grid market, really the backup port is only for backup. It's not for connecting more generation too. So it's very important to understand that. You don't have to use a proprietary solution. So I've got lots of different brands of inverters and batteries and smart energy systems throughout, and they all work together based on those simple principles of frequency shift, power control, and to some extent the big system with managed AC coupling. So thanks everyone. Just a last plug for my channels. Please, if you enjoy watching these Toolbox Tech Talks each Sunday, give us a thumbs up. There'll be more to come, and I'll be going back to interviewing guests soon. I've been having a little break from guests and just doing one-offs, which are a bit more in-depth and a bit more technical. But I will be going back to guest mode and introducing some key people in our industry and talking about their products. So once again, thanks everyone, and see you next Sunday, same time, same place. Okay, and we're out.